Yeah, good morning and good afternoon, everyone. Thank you so much, Lydia. Thank you so much, everyone, for joining this webinar. And please don't hesitate to ask all your questions. I will be very happy to address them. So, this webinar is going to address stability analysis in time domain. In this webinar, we'll explore how to measure the loop stability, bandwidth, and phase margin in time domain. We'll also discuss the influence of the output capacitors and load transient optimization. Finally, we'll demonstrate how time domain analysis provides an intuitive and more practical way to verify and guarantee the stability of automotive power solutions. So let's get started. So why do load transients matter in automotive? So typically load transients refer to sudden and significant changes in the current demanded by the load. These are critically important in modern vehicles due to increasing complexity of the electronic systems. Think about ADAS systems, infotainment, or powertrain control. These aren't just luxuries anymore. They are integral to vehicle operation and safety. So load transients matter a lot. So why do load transients occur, right? So these load transients aren't random. They occur due to real-time system demands. For instance, when an ADAS module activates, when you turn on your headlights or engage electric power steering, these actions can cause current demands. So why does this matter? If regulation in the power supply isn't stable during these transients, the consequence can be very, very severe. This can lead to malfunctions in critical systems, data corruption, or even system resets, which are unacceptable and potentially dangerous in automotive environment. The diagram of the car here illustrates the multitude of modules. For example, cameras, radars, and central compute, all of which can draw sudden current, creating these very high fluctuating load transients. And on the right bottom, you can see an example load transient waveform with a sharp load step, which is represented in green. And you can see the voltage excursions like the undershoot and overshoot represented in blue. Therefore, it's absolutely crucial that system designers ensure their DC-DC converters are stable during dynamic load transient conditions. So given the importance of stability, let's define what we mean by control loop stability in the context of DC-DC converters. Control loop stability refers to the system's ability to maintain a desired output despite external disturbances or changes in system parameters. For typical DC-DC converters, we are talking about maintaining a stable output voltage even when the load current fluctuates a lot. So the key parameters that define stability are the bandwidth, the which is also called crossover frequency, phase margin, and the gain margin. So on the right here, you can see what is called a Bode plot, which shows all these parameters. So first, let's start with bandwidth. So the bandwidth indicates how fast the system reacts to system transients. For typical automotive applications, the automotive bandwidth target is between 1/10 and 1/5 of the switching frequency. Second, phase margin. Phase margin indicates the system stability. The acceptable phase margin for typical automotive applications is 45 or greater. Finally, gain margin indicates how much the control loop gain can be increased before the system becomes unstable. It's another measure of how much robustness the system has. A typical gain margin for a stable system in automotive is equal to or lesser than minus 10 dB. Now that we understand the key parameters, how do we measure them? The traditional method is in the frequency domain, typically using a frequency response analyzer. The idea here is to inject a small AC signal into the feedback loop of the DC converter, DC-DC converter. It must be small enough to avoid non-linearities in the system and then measure the gain and phase response across the range of frequencies. As shown, one can connect the frequency response analyzer input channel A and channel B to the injection point in the feedback loop, and the injection point is created by having an injection resistance, which is in terms of tens to 20 ohms. The advantage of this method are very clear. It provides a clear visualization of frequency response, allowing for easy and precise determination of bandwidth and phase margin directly from the Bode plot. However, there are also disadvantages. This method can be prone to noise and non-linearities in the system, which can distort these measurements. It is primarily applicable for linear time invariant systems, which isn't always true for power converters with nonlinear control schemes like constant on-time control. And these analyzers are often expensive and require specialized capabilities. An alternative and often more practical approach, especially for real-world validation, is to access loop stability in time domain. In time domain, we typically look at the power supply transient response to a sudden load step. This involves applying a sudden change in load current and observing the output voltage response using an oscilloscope. As you can see, the setup is simpler. A DC-DC converter, a FET with a pulse generator, and an oscilloscope to measure the current and voltage. That's all you need for your load transient setup. The primary advantages of the time domain measurement are its ease and speed. One can get a quick visual measurement just using an oscilloscope. It directly shows converter dynamic responses and behavior to its real world stimuli. Importantly, it also applies to both linear and nonlinear systems, making it more robust for complex power conversions. The main disadvantage is that interpreting these waveforms require good knowledge and experience. So in this today's webinar, we are going to learn how to interpret these waveforms in time domain. So before going deep into a time domain analysis, in today's webinar, we are going to take MPQ 4385, which is a 42 volt, 25 amp, ultra low IQ synchronous buck converter with zero delay PWM control and quiet FET as a practical example. The MPQ 4385 supports a wide Vin range from 3.3 volts to 36 volts and capable of handling load dumps up to 42 volts. Thanks to MPS proprietary zero delay PWM control strategy, the MPQ 4385 has an extremely fast load transient response with reduced Cout and provides 3 times improved transient response versus peak current mode control. Ultra low RDS on using MPS bipolar CMOS DMOS process provides high efficiency, almost greater than 95% at 25 amps. The MPQ 4385 is scalable and multiphasable up to 200 amps. The MPQ 4385 is also optimized for low EMC and EMI performance with symmetrical V-in pinout placement with low noise, quiet FET, advanced switching technology, and frequency spectrum modulation. Please contact your local MPS representative for more details about MPQ 4385 if there is any interest. So let's talk about zero delay PWM control. ZDP is MPS proprietary fixed frequency control scheme for superior load transient performance and output capacitor savings. ZDP bypasses the error amplifier by connecting the feedback node directly to the PWM comparator, creating a fast path to the PWM comparator. This fast path quickly changes the duty cycle that drives the high side and low side MOSFETs to compensate for Vout fluctuations without ramping up the compensation up and down. For example, when Vout decreases due to a sudden load step, the duty cycle increases during the next on cycle to provide power to the output capacitors to recover the Vout. Zero delay PWM trademark achieves this without adjusting the switching frequency. A slow path using an error amplifier improves regulation accuracy as well. This slow path uses V feedback minus V ref to create an error signal. This signal is summed with an AC coupled current signal and a slope compensation ramp. Then this sum signal is compared to V feedback, which is fed into a PWM latch block that uses as fixed frequency clock as a reset signal. So overall, with this control scheme, ZDP can provide fixed frequency for power supplies. It improves transient response compared to common fixed frequency control methods like voltage mode control or peak current mode control. So there is an interesting app note about zero delay PWM control at monolithicpower.com website. And here is the app note details for more details on zero delay PWM control. So since we spoke about zero delay PWM control, we just want to show an example of how zero delay PWM control reduces the output capacitor through a low transient waveform. So in this waveform, we are comparing our MPQ4385 with zero delay PWM control scheme to a competition which has a peak current mode control. So in this example, we are doing a 0 to 12 amp load step. And as you see here, with 2 times 47 microfarad, the MPQ4385 has plus or minus 3% tolerance, but the competition with peak current mode control has roughly twice the undershoot and overshoot what we see on the 4385. To meet the same amount of undershoot and overshoot, the competition requires 4 times 47 microfarad at the end to meet the 3% tolerance requirement. So for MPQ4385 reduces footprint by 16 millimeter square, which translate into BOM cost savings. Let's take a quick peek at the MPQ4385 evaluation board and schematic before diving deep into our time domain analysis. The image on the left shows a compact evaluation board of the MPQ4385, showing a very small area, roughly around 300 millimeter square. This small footprint is a significant advantage for space constraint application. So now let's discuss the components that influence the uh, regular DC-DC control loop stability with respect to MPQ4385 as an example. First, the output capacitors. A higher Cout typically leads to higher bandwidth and the lower Cout results in higher bandwidth. Inductor L1. The lower inductor leads to higher bandwidth and conversely, an higher inductor results in a lower bandwidth. Switching frequency also plays an important role in the control loop stability. In this example, R3 here sets the switching frequency for the MPQ4385. Lower switching frequency, like 400 kilohertz, allows for a larger inductor and higher output capacitors to maintain stability and performance. A higher switching frequency, like 2.2 megahertz, requires lower inductor and output capacitor, potentially reducing the overall solution cost and size. Finally, the feed-forward capacitor, which adds a zero to the control loop to improve the converter stability. Let's focus on how we estimate phase margin from time domain response, specifically by observing ringing. When a load transient occurs, we often observe ringing on the output voltage. This refers to oscillations that occur before voltage settles back to its steady state. This ringing is a direct indicator of system damping. In time domain, the system's load step response indicates how fast the system responds to a sudden change. The nature of the response, specifically the ringing, tells us about the underlying phase margin. The relationship between ringing and phase margin is quite direct. A lower phase margin results in more ringing and a longer settling time, indicating less stable, more oscillatory system. On the other hand, a higher phase margin results in less or ideally no ringing and a smaller settling time, signifying a stable and a well-damped system. The graph on the right here beautifully illustrates this relationship. One can see the responses for various phase margins in this case. At 10 degrees phase margin, we have significant and prolonged ringing. As the phase margin decreases, as phase margin increases to 25, 45, and 76 degrees, the ringing dramatically reduces, eventually leading to a critically damped or even over damped response with no oscillations in this case. The table further quantifies this, showing that a 10-degree phase margin can lead to 7 output rings, while a 60-degree phase margin or greater results in no rings at all, which corresponds to an overdamped response. Let's now look at a practical example of how we can use the time domain to quickly access the phase margin. Here, we have a setup with a specific operating condition: input voltage of 12.5 volts, output of 5 volts, switching frequency of 2.2 megahertz, an inductor of 220 nanohenries, and output capacitance of 2 times 22 microfarads. We are observing an V out AC response to a load step from 10 to 20 amps at a specific slew rate of 10 amps per microsecond. Here you can see an overall load step transient. The yellow trace on the bottom indicates the load step, that is 10 to 20 amps at 10 amps per microsecond, and the green here represents the V out AC couple, showing the undershoot and overshoot. So zooming in into this undershoot, what's immediately apparent is that after the initial voltage drop due to the load step, the output voltage rings up and then settles, exhibiting only one ring of overshoot before stabilizing. This one ring behavior is very useful visual indicator in time domain analysis. For many power converter designs, particularly switching regulators, observing a single overshoot cycle before settling is a strong indication of a critically damped or a slightly underdamped response. Based on the relationship between phase margin and ringing that we discussed in the previous slide, this one ring characteristic typically corresponds to approximately 45-degree phase margin. A 45-degree phase margin is generally considered acceptable stability for most power supply applications. And it also indicates a critically damped response, which means the system settles quickly with minimal oscillations. So this is often a sweet spot for designers, offering a good balance between fast transient response and stable operation without excessive ringing. Beyond phase margin, the time domain can also offer insights into another critical parameter called the bandwidth. The DC-DC converter bandwidth can also be estimated directly from a low transient waveform, as it's closely related to how fast the converter responds to changes in time domain. One quick estimation method, particularly useful for oscillatory systems, is to use a ringing frequency itself. For example, in this particular case, we see a ringing frequency for approximately 240 microseconds, which corresponds to a bandwidth of 4.3 kilohertz, highlighting the inverse relationship between time and frequency domain parameters. However, it is important to note a limitation. This method becomes less reliable for systems that are critically damped or have very high phase margin, as the ringing may be minimal or absent, making it difficult to measure the ringing frequency accurately. So how do we overcome this limitation? There are some other ways to measure the bandwidth that is applicable for all the phase margin cases. So in this webinar, to measure the bandwidth in time domain, we'll be talking about response time method and undershoot based energy method. Continuing our discussion on deciphering converter bandwidth in time domain, we'll now focus on a practical and widely used technique for estimating bandwidth, the response time method. This approach directly links the speed of the converter transient response to its effective bandwidth. Let's define response time, or TR. TR is the time it takes from the output voltage to transition from 10% to 90% of its final steady state value after a step change. This 10% to 90% transition time is a standard metric for quantifying the speed of system response. Specifically, notice the blue arrows indicating the response time for a load transient. This visually demonstrates how we can measure the response time from the transient waveforms. For power converters that are well compensated, we can use a simple equation. The bandwidth is approximately 0.35 divided over the response time. This formula provides a quick and useful estimate for system control bandwidth from a time domain measurement aspect. But it's also important to understand the theoretical basis for this equation. So it is derived from the fundamental relationship between the rise time and the bandwidth in an ideal first order system. While a typical buck converter is a complex system with two poles, a well compensated one can often be accurately approximated as a first order low pass system for the purpose of bandwidth estimation, making this an effective and practical shortcut bandwidth estimation method. Now that we discussed the theory behind the response time method, let's look at a real world example to see how it is used in practice. This slide presents an actual measurement of MPQ 4385. So, assuming the same test conditions that we use for our phase margin analysis and zooming into and we have a loads 10 to 20 amp load step with undershoot and overshoot on a V out and zooming into our undershoot waveform. Here we have identified our 10% and 90% points of output voltage recovery. As defined earlier, the time taken for the voltage to transition between those 2 points in our response is this response time. In this specific measurement, we can clearly see the response time is measured close to 1 microseconds. Let's put our measured response time in the formula that we discussed earlier. We have a precise response time of 1.1 microsecond. So bandwidth calculated is approximately 331 kilohertz in this case. This calculation provides a very good indication of converter's control loop bandwidth based purely on its time domain performance. Another technique for time domain bandwidth analysis is undershoot based energy method. This method leverages the energy deficit during a load transient to estimate the converter bandwidth. When a DC-DC converter experiences a sudden increase in load current, its output voltage will momentarily dip. This undershoot is a direct result of output capacitor not being able to supply enough charge quickly to meet increased demand before the control loop can fully react and regulate the output voltage. So on the right, you can see an oscilloscope capture, which visually represents the key elements of the undershoot-based energy method. So during the load step, we observe a momentary dip on the V out. This dip occurs as the capacitor C out is discharging to supply the increased load current. After the undershoot, the control loop engages and the converter recovery phase begins, where the output voltage is brought back to its regulated value. This method lies in connecting this observable undershoot to converter bandwidth through a relatively simple equation as shown below. This equation states that the undershoot uh, delta V out is proportional to the change in load current, delta I out, and inversely proportional to two key parameters, the output capacitance and the crossover frequency, which represents the loop bandwidth that we are trying to determine. This equation is essentially derived from the capacitor charge current equation, which can be estimated from the following: I equal to C dV by dt, where dt is 1 by 2 pi f naught. And rearranging for delta V out, we arrive at this equation. Let's apply the undershoot based energy method to a practical example. Again, same test condition. We are looking at a load step of 10 amps to 20 amps Uh, so here the delta I out measured is 10 amps in this case. And based on the waveform, the undershoot measured is negative 188 millivolts. So using the equation and an initial assumption of C out of 2 times 22 microfarad, we get an estimated bandwidth of around 192 kilohertz. Notice this doesn't quite match the 331 kilohertz we got from the response time method. Let's see why the discrepancy in this method. This leads us to a very important point, the impact of the output capacitors. In our example, we are using two 22 microfarad 10 volts 1206 Murata caps that are connected in parallel. However, the actual capacitance significantly derates with DC bias rating. Looking at the Murata's graph, a 22 microfarad capacitor at 5 volts DC bias only provides about 13 points, roughly 13 microfarad of effective capacitance. This is a critical factor that is often overlooked when dealing with control loop designs. So, therefore, the actual effective capacitance for two such capacitors in parallel is effectively 26.4 microfarad. So, using this corrected output capacitor in our formula, the crossover frequency is estimated to be around 326 kilohertz in this case. This revised results now closely matches the bandwidth estimated from the response time method. This highlights a crucial design principle. Always use the actual effective capacitance when designing the control loop or performing loop-related calculations, and be sure to consider the MLCC DC bias characteristics. So let's summarize our time domain bandwidth analysis methods. We can estimate bandwidth from ringing frequency. This offers a quick visual feedback from the oscilloscope, but it's not suitable for critically damped or high phase margin systems. Response time method provides a quick visual feedback as well, and it's useful for real-time monitoring. However, it requires clean measurement without excessive noise or spikes for more accuracy. The undershoot-based energy method intuitively shows direct relationship between the output capacitors and the response time. The key here is that the requirement of sufficient and accurate information of output characteristics include DC bias rating, which is a must-have when dealing with undershoot-based energy method. Each method has its own strengths and weaknesses, but together they offer powerful tool for time domain analysis. Now, let's bring it all together and compare our time domain estimations with a traditional frequency domain measurement. On the left, we have the time domain response, which is a low transient response. And on the right, we see a classical Bode plot that is taken from a frequency response analyzer. For the same conditions with C out equal to 2 times 22 microfarad, in the frequency domain, we measure a phase margin of 46.7 degrees and a bandwidth of uh, close to 300 kilohertz. So in time domain, from the response time method, we estimated a bandwidth of around 331 kilohertz. From the undershoot based energy method, after correcting the effective capacitance, we calculated the bandwidth to be around 320 kilohertz, and we estimated our phase margin to be close to 45 degrees based on one ring. As you can see, there is an excellent correlation between these two domains. The bandwidth estimations are very close and the phase margin is consistent in this comparison. Now, let's expand onto this comparison by looking the impact of varying the output capacitance and how both uh, time domain and frequency domain analysis reflect these changes. So on the left, we have a time domain responses for different output capacitors value. So each waveform corresponds to different level of output capacitance and thus a different phase margin. So starting from the top with 3 times 22 microfarad, the waveform is well damped representing a good stability with a phase margin of around 60 degrees, and one can see no bumps or ring in this waveform. With 2 times 22 microfarad, the response is more controlled. The phase margin decreases to 45 degrees, which is considered acceptable, and one can see a single bump. With a single 22 microfarad, it shows some damping with a phase margin of around 25 degrees, but still it has poor stability, and one can observe close to 2.5 to 3 rings in this waveform. With a 10 microfarad cap, we are seeing very strong oscillations indicating instability and a very low phase margin around 10 degrees. On the right, we have a frequency domain plots, and what we see, each curve corresponds to the same capacitance cases. As the capacitance increases, the phase margin also increases, and the crossover frequency as the capacitance increases, the phase margin also increases and the crossover frequency decreases, all consistent with our expectations. Sorry. So now at the bottom, we can compare our results numerically. We have extracted phase margin and bandwidth from both frequency and time domain. So one can also see that there is a strong correlation across all these methods. For example, with 3 times 22 microfarad, time domain analysis estimates bandwidth to be around 215 to 216 kilohertz with a phase margin greater than or equal to 60 degrees. In the frequency domain, we measure the bandwidth and crossover to be 224 kilohertz and 60.3 degrees respectively. Even for the 10 microfarad case, both methods estimate close to 700 kilohertz of bandwidth, and phase margin is low in both the analysis, which is close to 10 degrees. So the key takeaway here is that like in time domain analysis using load transient, it's offer a quick and reasonably accurate estimations of stability and bandwidth. This is essentially helpful when Bode plots aren't feasible or available. We have now discussed how to analyze the transient response and estimate bandwidth and phase margin in time domain. Now let's shift our focus to transient response optimization in time domain. So many modern DC-DC converters are internally compensated for simplicity and ease of use. This often means internally compensated converters might not be optimized for applications, potentially leading to a slower load transient performance during the load step. With the same conditions as discussed before, the scope capture shows a 45-degree phase margin because of one ring with almost close to 450 millivolts on the undershoot and overshoot during a 10 amp per microsecond load step. VO triple greater than plus or minus 5% is typically not accepted in automotive off-battery buck converters like MPQ4385. The question then becomes how the transient response can be improved. The key component here is the feed-forward cap. The feed-forward cap is placed strategically within the feedback network. This capacitor plays a crucial role in shaping the frequency response of the control loop, allowing us to boost the converter bandwidth while maintaining a sufficient phase margin for stability. The CFF introduced a zero in the feedback loop transfer function, providing a phase boost. This phase boost is maximized in a region between the places where the pole and zero frequencies are introduced, which helps to counteract the phase lag. The feed-forward capacitor is usually placed in parallel with the top feedback resistor, which is R1 in this case. This placement is critical for introducing the desired zero and pole into the loop transfer function. So, after we place our feed-forward cap, the location of zero, Fz, is determined by the values of the feedback resistor network R1 and the feed-forward cap CFF. As shown in this equation, the zero frequency is inversely proportional to R1 and CFF. This gives us design control over where the phase boost occurs. In conjunction with the zero, a pole is also introduced, which is determined by the feedback resistors R1, R2, and CFF, which is shown in equation 2. While the zero provides the phase boost, the pole ensures that the gain roll-off is still controlled at very high frequencies. It's also important to note that while boosting bandwidth is desirable using CFF, there is a limit as well. Using a CFF that's too large can lead to excessive bandwidth, which can actually degrade stability by significantly reducing the phase margin, potentially even causing oscillations. Careful design and measurements are essential to find the optimal CFF value. This slide provides a more step-by-step practical example. We'll walk through a design procedure to determine the appropriate value for CFF in a real-world scenario. So let's go through design procedure steps. The first step in designing the feed-forward capacitor is to establish our baseline feedback network. This typically involves estimating or selecting our feedback network values, the voltage divider resistors, to set the desired output voltage. In our example, based on MPQ 4385 schematic for 5 volts output voltage, R1 is 100 kilo ohms and R2 is approximately 19.1 kilo ohms. Next, we need to understand the converter bandwidth before adding any compensation or feed-forward cap. This is our starting point. In this specific example, without the feed-forward cap and using the response time method, we estimated the bandwidth to be around 139 kilohertz. To effectively place the zero on pole introduced by CFF, we consider the geometric mean of the zero on pole frequency. This geometric mean provides a good estimate for the frequency at which the zero has to be placed. A useful design rule of thumb is to set the geometric mean frequency equal to the converter's original crossover frequency without the CFF. This helps ensure the phase boost is introduced at the right point to extend the bandwidth effectively. So one can see the equation here that geometric mean of pole frequency times the zero frequency is equal to the crossover frequency that we have estimated. So using the equations for zeros and poles that we discussed in the earlier slide and also plugging the value of our estimated bandwidth into this equation, we end up calculating CFF to be around 28.6 picofarad in this case. So rounding the CFF to the nearest standard capacitance value, we'll take a CFF of 33 picofarad in our example. So we added a 33 picofarad CFF to our parallel to our top feedback resistor. So on the left here, you can see two sets of waveforms. The blue one indicates the waveform with CFF and the green one without the CFF. And here we are zooming into our undershoot. So comparing the scope captures with and without the CFF, without the CFF, one can indicate that there is a slow recovery and potentially more significant undershoot, indicative of a lower bandwidth that we calculated earlier. With the CFF, the difference is striking. We see a much faster recovery from the load step and the output voltage settles significantly quicker. Specifically, the response time is just reduced to just 1 microsecond, a clear improvement that the no CFF case, which corresponds to bandwidth, and this corresponds to a bandwidth of 340 kilohertz. Further, the phase margin is now excellent in the excellent range of 55 to 60 degrees. because we don't see any bumps in this area, maybe a minute bump. So this corresponds to a phase margin of around close to 55 to 60 degrees, indicating good stability. To understand why this improvement occurs, let's look into the frequency response plot. This Bode plot illustrates the impact of feed-forward capacitors on the control loop perspective. The green trace here represents the loop response without CFF. Observe its bandwidth indicated to be around 129 kilohertz and phase margin of 45 degrees, which closely matches with whatever we estimated with no CFF case through time domain analysis. So the blue and the red waveforms are the gain and phase plots for this CFF case, and the bandwidth and phase margin corresponds to approximately 312 kilohertz and 55 degrees respectively. The direct consequence of increased bandwidth in this case is that we can observe a faster transient response as we observed here. The key to this improvement is the strategic placement of zero roughly between the 40 and 50 kilohertz frequency range. This bump in the phase response where the phase margin is boosted is precisely good stability. This zero is responsible for a crucial phase boost, counteracting inherent phase lags in the system. The result is that the system's gain margin remains high for a longer time, allowing the bandwidth to extend at a much higher frequency and roll off at a higher frequency, as we are seeing here, while maintaining a very good phase margin. So the direct consequence of this increased bandwidth is a significantly faster transient response. As seen in scope capture, it has a roughly 2 times faster transient response when compared with the no CFF case. While CFF is beneficial, its selection isn't arbitrary. There are critical considerations in designing a CFF. The placement of zero and pole demonstrated here is generally considered optimal for many power converter applications, balancing speed and stability. So increasing CFF increases the bandwidth, resulting in a lower overall phase margin. So decreasing CFF has the opposite effect. If CFF is too small, the zero and pole frequencies will be pushed too high, resulting in no performance improvements on the bandwidth and phase margin. So by adding an external CFF, designers can fine-tune the control loop and optimize their performance. To wrap up our discussion, let's summarize the key takeaways. The table here neatly summarizes the type of information one can get from frequency domain versus time domain analysis. While frequency domain gives direct phase margin, gain margin, and loop bandwidth, the time domain provides critical insights into undershoot, ringing, and overall voltage behavior, which directly translate into system stability performance. So, a quick and practical method for loop response estimation is to measure the load transient directly in time domain. The phase margin in time domain can be estimated by observing whether the response has been damped or oscillatory behavior. Less ringing indicates higher phase margin and better stability. The control loop bandwidth can be measured in several ways, but the estimations based on the response time method and the undershoot based energy method correlate closely with traditional Bode measurements. So a fast load step is always required. A fast load step is always required to stimulate the control loop. Load steps that are too slow cannot stimulate the control loop across a sufficiently wide frequency range. So a recommended rule of thumb for a load step is use a load step with rise time much greater than 1 over the bandwidth frequent crossover frequency for detecting stability problems in DC-DC converters. The effective output capacitance plays a critical role in the control loop. Always use actual effective capacitance in your control loop or design calculations. By adding an external feed-forward capacitor, designers can fine-tune the control loop and optimize the performance for internally compensated DC-DC converters. So, thank you for your attention today. I hope this provided a clear understanding of stability analysis in time domain, the influence of output capacitors, and CFF selection for improved load transient performance. I am now happy to take any questions you may have.
Thanks a lot, Kashyap. Great presentation. So just remind everyone you can scroll over the bottom of your Zoom webinar interface and you will see the Q&A button. So feel free to type in any questions you might have. With that, I will turn over to Garrett so we can start with the first question.
Yeah. Hey, Kesha, thank you for the presentation. I think one of the common questions we're seeing here is what should the amplitude and the slew rate of the load step be to get realistic estimations of the crossover frequency and the phase margin?
Yeah, so as discussed earlier, like in our summary slide, so load steps that are too slow cannot stimulate the converter loop across a sufficiently wide frequency range. So this might not critically highlight or indicate stability problems. So the main goal for the slew rate and the amplitude is to excite the loop near the crossover frequency. That should be our goal. So a fast load step between 20 to 80% of full load current and with a rise time that is greater than 1 over the crossover frequency should be used for detecting stability problems in a typical DC-DC converter. So for example, if a part is rated for 10 amps, one can consider a load step amplitude of 2 amps to 8 amps and a slew rate between 1 amp per microsecond to 10 amp per microsecond, which is common in all of the automotive applications nowadays.
And then the other question I have here is, can this be applied to other types of topology? I know we were talking about constant frequency here, but can this be applied to constant on-time control as well?
Yeah, so yes, it's definitely applicable for constant on-time buck converters. So if you look at the constant on-time buck converter control scheme, uh, it uses a constant on-time pulse and adjusts the off-time based on output voltage feedback. And also the COT control lacks a traditional linear compensator as the feedback or Vout is directly fed to the PWM comparator and a ramp injection is used for stability. So these components create nonlinear blocks and Bode plots on nonlinear systems is not really essential or useful. So practical time domain measurements with fast load step is definitely valid for nonlinear control schemes like constant on-time control.
Okay. And then the last one I have, if you're looking at the ring frequency to get the phase margin, and let's say you have a little bit of different frequency in each of the rings, which one should you use to estimate the phase margin?
Yeah, so that's a good question. So actually, the first dominant ring in the waveform should be used to estimate the bandwidth or the crossover frequency. This is because typically the highest frequency ringing, the first ring is always the highest frequency ringing, and it's most closely related to the control loop bandwidth. So the other ringing that follows the first dominant rings can be from various sources like secondary poles found by the output LC filter in a buck converter or any other power converters, or some ringings might also happen due to parasitic resonance from PCB trace inductance or some or just or being harmonic content from the load step. So it's always good to take the first ring into consideration for estimating the crossover frequency.
Okay, so I know our time is limited and for the unanswered question, we're going to note them and get back to you through email. So thank you, Garrett. Thank you, Kashyap. As I mentioned before, the presentation and the link to the on-demand version of the session will be sent out the next few days, so you can review it at your own convenience. If you are interested in more webinars like this, feel free to check out our website, monolithicpower.com/support/webinars. So stay tuned for our future webinars. We have plenty of interesting topics coming up. And yeah, with that, I would like to thank you for joining our webinar today. We hope to see you again soon in one of our future ones. Thank you. Have a great day, everyone.